my pleasure to introduce Christopher Voll to give our third of these lectures, and he'll be giving a sequence as well, so it'll be built in. And it's also his first time in the US, so I'm very glad that we were able to convince him to join us here, and also for the support all the way along, co-organizing this. So I can't remember your talk title, but it must have had tensors and enumerative algebra in it. Is that correct?
Well, you made up a title, and
and that was very helpful.
And yeah, it was actually. It helped me focus.
Okay, take it away, Christopher.
Thank you, James, for the kind introduction, for the title that you made up. I think it was something about Pfaffians and Determinantal varieties and Tensors or something. So that I think that put me on the right track. Yeah, so it is the first time I'm here. I think I've known James for 8 years or something. We met in Oberwolfach, and earlier this morning I was having coffee. I was having small talk at the coffee urns, and there were two young colleagues, and one of them said, "Oh, I'm now working at X university," and the other guy said, "Oh, that's interesting. Are there any tensor people there?" And I thought, if that place had been Bielefeld, which it wasn't, would I have said there are any tensor people in Bielefeld? So what I want to try with these 3 lectures, I want to suggest that maybe there are some tensor people in Bielefeld, and while you work out where Bielefeld is, it's a small town in a middling country in a different continent, I will give you an idea what I want to talk about on Wednesday, Thursday, and Friday. Today, that is Wednesday, I want to, in a way, explain why I'm here, explain something about what has sustained conversations with James, but also with other people who have taught me patiently that the reason I find the things that I do difficult is because tensors are difficult, and that I might benefit from learning a few things about tensors in the things that I care about. So today I will tell you why what I care about is maybe related with tensors. Tomorrow we will take a, if you wish, geometric point of view. I will try and convince you that some of what we care about in enumerative algebra is related to the complexity of singularities of Pfaffians and more general determinantal varieties. And thirdly, I would like to take an arithmetic point of view and give an inkling why some of the reasons people get excited about tensors in enumerative algebra have a very arithmetic flavor to them. But let's take things in order. Today is Wednesday, so I think today I owe you an answer to at least 2 questions, which I pose. And the first thing is, what is enumerative algebra? What does he mean by that? And second, what on earth is this to do with tensors? Yeah, so this is what I want to do today. So today, 2 questions. First one, what is enumerative algebra for the purpose of this talk? And secondly, what's this to do with tensors? So in Denver, I was asked, what's your reason for coming to the United States? And I was told not to make jokes with these gentlemen before, so I did not say, yeah, whatever I could have said. So I don't give you that answer. I want to answer these questions. Yeah, that's why I'm in the United States. What is enumerative algebra? Well, I mean, James, you didn't define what a tensor was, right? I mean, you told us something about tensors, and then I don't know. I don't think you at the end there was something that looked like a definition. I'm going to do something similar. I will not define enumerative algebra for you. I will take you right into the flow of things that excite me. So, towards an answer towards this first question, I want you to think of an algebraic object of your choice. So let's say a group. Typically, in my line of work, these are infinite groups. Sometimes they're profinite, sometimes they're arithmetic, but typically they are infinite groups. And often we are in a situation where we associate with G, with this group, data. Can I call this data? I just do it. Yeah. So the data that I or people in my community often look at comes somehow pre-sorted as a sequence. So this is typically a sequence of integers or rational numbers. So that's some sequence of rational numbers, or more often than not natural numbers. And the paradigm is you learn something about G when you understand something about the sequence. And I will become more precise in just a minute, but let me stay on this meta level for just a few moments. So the idea is this is data about G, and the hope is that we advance the world's knowledge about G when we know anything about D. And then more precisely, I want to understand maybe sometimes asymptotic properties of these data. Like, for example, if these are natural numbers, how do they grow with n? Yeah, do they grow exponentially, polynomially, whatever? And sometimes I'm interested in finer arithmetic properties. What can you say about the prime divisors of these numbers? Can you say something about algebraic or even linear recurrence relations between these numbers? Yeah, these are the kind of questions that often start us off on various journeys that will get us to tensors. So let me say, so when we have a counting problem, what do I mean by a counting problem? For the purpose of this morning's lecture, a counting problem is nothing but a pair consisting of, let's say, a group G for simplicity's sake, and an interesting sequence encoding something about this group. And often what we do then is we try and keep up with the number theorists who pioneered more than 100 years ago the idea to take data like this and encode it in a suitable generating function, and then use the right generating functionology, as Wilf would say, to study these data and then kind of get information about G. And it turns out in the circumstances that I'm mostly involved in, it is not an ordinary or exponential generating function, but the kind of Dirichlet type generating functions that are most promising. So we take this data, dn, and we think of this as the coefficients of a Dirichlet type generating function. And we call this the zeta function associated with G and the sequence dn. Yeah? So the zeta function of this counting problem is nothing but this formal Dirichlet series, which I will call ad hoc the zeta function associated with this counting problem. I call this the zeta function because many zeta functions that people come across in algebra and geometry have exactly this form. If you think about the Dedekind zeta function of a number field, it does exactly that for the, not a group, but a ring of integers of a number field, and dn, the number of ideals of finite index. And there are countless examples of this form. And why do we do this? Well, it pays off. Yeah? Dedekind showed us that understanding the analytic properties of this formal series tells you something about the number field. Yeah? There's something called the analytic class number formula that says if you understand Dedekind's zeta function at s equals 1, you understand an awful lot about the number field. Yeah? You know the class number, the regulator, number of complex and real embeddings. So these functions have a good track record of unveiling information about the counting problems that they are associated with. And now I will become less hand-wavy and be more precise. I will concentrate on two kinds of counting problems that I will be revisiting throughout my lectures to try and convince you that tensors are really what's at the heart of the counting problems that I'm interested in. So we have two kinds of counting problems. The first one I want to call normal subgroup growth. So if dn is what in the literature is often called an with a normal subgroup symbol superscript, if this is by definition the number of subgroups of G which are normal and of finite index n, then we get a sequence of maybe finite or maybe infinite numbers, certainly integers or infinity, and understanding this, the properties of the sequence A and normal is what people in asymptotic group theory call the normal subgroup growth.
So
of G.
Is there an a priori reason to think that's a finite number?
In general, of course not, no. If G is finitely generated, then it's an exercise, James, to prove that this is a finite number. But in general, it's not. So all the groups, and I know people will be disappointing, all the groups that I look at have a very finitary flavor to them. So if G is finitely generated, and we will become much more restrictive in a minute, but then this is a finite number. Yeah? Okay, the second kind of counting problem, maybe I should say one thing. So subgroup growth is the title of a volume of a book by Alex Lubotsky and Dan Siegel, two of the people who put this topic on the map in the 1980s and 90s, and wrote a definitive monograph on this subject. So that's very much in asymptotic or asymptotic group theory a traditional topic. The second class of counting problems I want to throw at you is the one that doesn't count subgroups of a given group, but representations of the group. Yeah? So we will be counting in a minute representations of our group G. Let's say for simplicity, complex irreducible representations. And I will put off for a second to define what I mean. I will be looking at classes of groups where, James, this number is not finite. But there's a natural-ish equivalence relation which sorts these infinitely many representations into finitely many equivalence classes. So I will make sure that this gives that this makes a well-defined counting problem.
N is allowed to vary in that, right?
Sorry?
Your N is allowed to vary.
That's the point. It varies. Yeah. So let me write Rn tilde for reasons that hopefully will become clear later. For the number of n-dimensional complex irreducible representations, maybe up to some equivalence relation. Yeah? Okay, if this is your counting problem, you are in the realm of representation growth. And if you ask Math Silent about representation growth, you probably come across seminal papers by Larson and Lubotsky, by Chaikin, Sapirain, by Nir Avni, and his collaborators. So that's a comparable but comparatively new area in asymptotic group theory. Okay, I think I owe you an example. I'm driven by examples, and I hope that you enjoy looking at some of the examples that I brought along with you. I want to start very simple. What did I say? I want an infinite group. What's the simplest infinite group? Well, it's the infinite cyclic group, which you allow me to call Z for the time being. So what's the normal subgroup growth of the infinite cyclic group? And these are fancy names that really mask a first or second year exercise. Yeah, you already solved it, James. At some stage, undergraduates learn that the infinite cyclic group has a unique subgroup of each finite index. Yeah, namely the group of integers divisible by n for each n. So, the zeta function solving the normal subgroup counting problem of the infinite cyclic group. What is it? Well, I look at my recipe. I look at the Dirichlet generating functions with the dn's as coefficients. Dn is 1 for each n. That's a unique subgroup of finite index n, namely the integers divisible by n. So I'm just writing down what the world knows as the Riemann zeta function, and often denotes by zeta s. Yeah? So that's the Riemann's famous zeta function. Well, you would say, I mean, the constant sequence 1, I don't need some fancy analytic number theory to look at. And what do you say to that? You said, yeah, well, the Riemann zeta function is not really interesting because it doesn't tell us something about the constant series 1. Yeah, well, I mean, there are other reasons maybe to care about the Riemann zeta function, yeah? If you know the analytic properties of this zeta function, then, yeah, what did you say? I mean, don't tell Netflix, just do your own business, yeah? So if you know the zeros of this zeta function, don't tell me, don't tell anybody, yeah? You just get on and you Google why this is important. So the point is, this is an interesting function, not becomes from a complicated generating function. It solves a complicated counting problem because it doesn't. It's interesting because of its arithmetic and analytic properties. Yeah? In particular, we teach our first or second years that this zeta function has what we call an Euler product indexed by the primes into functions that are rather much more simple. Yeah, so, and what's behind that is essentially the fundamental theorem of algebra. Yeah? Every natural number n I can write essentially uniquely as a product of the primes dividing it. Yeah? And if you don't care about convergence for a second, and this second can take a long time, then this identity is essentially this unique factorization. So the point what I want to make is we have a global object here that, so I think a number theorist would be happy if I called this a global zeta function. And we write it as an infinite, it's defined as an infinite sum, yeah? Okay. But it also is an infinite product of rather harmless, wouldn't you say, local zeta functions. And when I say locally harmless, then I mean 1 over 1 minus x doesn't get much simpler in terms of generating functions, yeah? You agree? Very good. You've seen worse, yeah? You have seen much worse things. Good. So, all that kind of faffing about in order to tell you about the Riemann zeta function? This can't be. No, it isn't. I want to tell you about something else. Do I? I don't want to get drawn into analytic properties. I mean, you see, one of the reasons people interested in subgroup growth dug up this number theoretic tool, because if you know where this formal thing converges, you know how these coefficients grow. Yeah, that's standard Landau type analytic number theory. So maybe there was some hope that by writing down the zeta function and knowing where exactly the abscissa of convergence is, we could learn something about the growth of these constants. This is difficult territory, and I will stay away from it because it doesn't lead us to tensors, which is where we want to go. This is why we want to enter the United States. Okay. I didn't tell you about the representation growth problem for Z. Maybe I should. Maybe we should talk about this. So, what are the irreducible n-dimensional representations of the infinite cyclic group? Well, as so often in life, it depends. Yeah, it depends what n is. Yeah. If n is larger than 1, there aren't any, and if n is 1, there are many. Yeah, there are infinitely many. So here you see, even for the infinite cyclic group, this is not a reasonable counting problem unless we kind of pool representations together. And I will be precise about what I mean by this in a minute. I want instead introduce you to a running example that I plan to come back to during my lectures over and over again. And that's a group that is a tiny bit more complicated than this infinite cyclic group, and that is the discrete Heisenberg group. So another example I want to invite you to look at with regards to normal subgroup and representation growth, and that will get us to tensors, is the Heisenberg group, discrete Heisenberg group. And what is this? This is nothing but the group of 3 by 3 upper unit triangular matrices with integer entries. Yeah? James asked me for a short bio for the website, so I thought I'd give you a short bio of the Heisenberg group, yeah? So that we, kind of a one glance CV, so to speak, yeah? So what we all should know about the Heisenberg group? Well, I put 3 copies of Z here, reflecting that there are 3 degrees of freedom, yeah? So in some sense, this is a 3-dimensional object. Dim of G is 3. And I put inverted commas here because I don't want to really talk about dimensions of finitely generated groups. But I will not put inverted commas around this statement. H is the Hirsch length of G. So that's the technical way of making this statement precise. The discrete Heisenberg group sits as a lattice inside the real Heisenberg group, and the real Heisenberg group is a real Lie group of dimension 3. Yeah, that's all I want to convey here. Of course, you see this, but I still want to write this down. This group is not abelian. We will see in a second how to do computations in this group, but first year exercise, this is not an abelian group, but it is a nilpotent group of nilpotency class C equal to 2. What does that mean? That means it has a commutator subgroup, which is not trivial. It actually is the matrices which have zeros on this off diagonal, but this commutator subgroup is central. Yeah. So to say that we have nilpotency class 2 is to say we're not abelian, but we're very close to it. So this is to say that the derived group is central. Actually, in this case, it is equal to the center. You recall the derived group is the subgroup generated by the commutators, and the center is the subgroup consisting of all elements commuting with all others. Yeah? So in this case, these two things coincide, and this will become important when I will bring in tensors to the scene in just a few minutes. So in fact, this observation here helps me to decompose this three-dimensional object into 2 objects of dimensions 1 and 2 respectively. Yeah? So I just said it, and we will see it in a minute. The center of G, that's just matrices which have zeros on the off diagonal and do whatever they want here in the northeast. That's a 1-dimensional object. Yeah? So the Hirsch length of the center is 1, and the Hirsch length of the quotient of G by G prime, in other words, the largest abelian quotient, is rank 2. Yeah? So I can think of these as the matrices where I kind of disregard what's happening in the center here. Yeah? So I have 2 degrees of freedom here. So the Hirsch length of the cocenter, as it happens to be, is 2. Please keep these things in mind. 1 and 2. Good. There was something to erase things, and yes.
There's 6 of them on the top of the podium as well.
Pardon?
On the top of the podium, there's a tower of them.
Excellent. Thank you. Are they single use? Do I throw them behind me?
Yes, right. Throw them at the
You can tell me anything about this country, right?
Yes, right. We call them rubber.
You can tell me anything, I won't believe everything. Very good. So when I prepared this lecture, I thought I should really be able to compute with these things. Yeah? So I invite you to join me on the pleasures of computing with elements in the Heisenberg group. Just to realize later that it's such a joy not having to do this. Yeah? So why don't we do this? So G continues to be the Heisenberg group, yeah? And G and H are 2 elements. And I want to I want to compute two things with you. I want to compute inverses and commutators. So okay, let's get going. So what is an element in the Heisenberg group? Well, it's a uni upper triangular matrix, and I only have to specify the entries here in the top. So let me write x, y, z for the integers that go in here. Little exercise. What is G inverse? Well, G inverse, you all know how to invert a 3x3 matrix, don't you? That's what I thought before I did it. So I'm tempted to write just, minus x, minus y, minus z. And that's actually not so far off. It's almost correct, only that it isn't. And it's incorrect in this 1,3 entry here, yeah? So it's minus x plus yz. So if you think of this as an element in z cubed, which you could, yeah? I mean, you just harvest these coordinates. Then the question is, how do you do group multiplication in these coordinates, yeah? And this computation shows that inversion is essentially flipping the signs here, but you have to correct a little bit in the last coordinate. If h is alpha, beta, gamma, I call these things, then of course I can have a formula for the inverse. But what I really want to note down is a formula for the commutator. So what's the commutator? The commutator is the group element G times H times G inverse H inverse. No, yeah, unless it isn't, yeah. But so where I come from, this is the commutator. It doesn't matter what it is. I mean, you just it does, yeah. Well, it does, but I'll fight my corner on that one. Anyway. Some people call this the commutator, other people don't. If you do this computation, and I did this waiting at the dentist, and it took me, I waited for a long time, and it took me a long time to get my mistakes right, but at the end, I was called to the dentist, and just before that, I could write down what this is. So this is x times alpha minus, x times beta minus alpha y. How about that? Yeah? Trust me. I've done this before. Yeah. So what is remarkable? So if it wasn't for this, yeah, then this commutator or this pseudo commutator would be 0. That would mean that G and H commute. Well, in general, it isn't, obviously. And fun fact, this here is a determinant. Namely the determinant of this 2x2 matrix, isn't it? Yeah, x beta minus alpha y. Okay, fun fact. So, in other words, G and H commute if and only if these off-diagonal entries here are linearly dependent. Yeah, that's one way to memorize this. If you don't want to do this computation yourself, and trust me, you don't want to do this yourself, then you could take this as a hint. Yeah. So I think I told you more than you need about the Heisenberg group for the time being, so that I can now without too much of a bad conscience introduce the class of groups that I want to invite you to study. I want to denote by T2 the class of class 2 nilpotent, finitely generated, torsion-free nilpotent groups whose derived group is central, is equal to the center. Okay, and if you're Martin or some other person, then you know what this means. And if you're not, then this is just a mouthful, and you should just think of things like the Heisenberg group. Yeah, the Heisenberg group is a prime member of this class of groups, and you will not miss much of what I'm going to say if you just think of the Heisenberg group. Yeah, this group of upper unit triangular 3x3 matrices over the integers. Note that I'm carrying around these integers in the notation. Yeah, And there's a reason for doing this, and I just rubbed it off. That's our project on Friday, to understand how the tensor-related questions that we're posing here change if we allow ourselves to play with this entry here, so to speak. But I'm getting ahead of myself. I want to bring tensors on the scene. I mean, they can't hide forever, can they? Let's keep the Heisenberg here in the corner. Sorry, the Heisenberg group in the corner. And let's try and address what I highlighted as the second question. What's this to do with tensors? Yeah, for that I want to invite you to take any element in this class of class 2 important groups, for example the Heisenberg group, and allow me to write down the following map. I want to write a map from the quotient of the group G by its center, I call this the cocenter, times itself, into the derived group. And how do I define this map? Well, I take elements G and H, or rather their residue classes modulo the center, and such a pair of classes of elements I map to their commutator. Well, a little thought why this is well defined. I mean, G bar is any residue, G is any lift of G bar in this cocenter, and that this is well defined is essentially the assumption that G is class 2 nilpotent. So I call this the commutator map. The commutator map takes two elements and assigns to them their commutator. Only we kind of divide out what is irrelevant for commutators, namely the center. Yeah. So in this lineup that I had before, so G bar would be essentially identified with that off diagonal x and y, yeah, and H would be bar would be identified with AB, the two alpha beta, the off diagonal elements here. And what did we just say? Well, we said the commutator of these matrices. Note that Z and gamma don't feature here at all, yeah, because they're irrelevant. We divided the center out. This gets mapped to x beta minus alpha y. Yeah. So for the Heisenberg group, this is what this map does. In general, this is obviously a bi-additive map. Yeah, it's if you wish linear, Z linear in both entries, and it's antisymmetric because no matter how you define the commutator, if you do it the other way around, you get the inverse. Yeah, that's the point. Yeah. So do I have to write this up? No. I risk making another faux pas. Yeah, you're shaking your head. I shouldn't. Yeah. The point is, okay, this is bi-additive, by which I just mean bilinear over Z, and antisymmetric. And yeah, and now there's a fork in the road. There's a fork in the road, and I have to go down one of the paths, which I will be doing. So what my objective today is, I would like to give you an idea why the following result is true. It's a result by Magid and Nunley from the 1990s. So let me write it as a proposition. They published a paper on this. Magid and Charles Nunley in the 1990s, I think 91, I'm not quite sure. So these two folks, they didn't talk about zeta functions. They just talked about representations of the Heisenberg group. I think the paper is called something like integral twist isoclasses of representations of the integral Heisenberg group. And in order to state their theorem, I have to explain to you what I mean by this tilde. You remember that I defined Rng tilde as the number of n-dimensional complex representations which are irreducible up to this equivalence relation. I owe you a definition of this. So what are elements in this set? Well, they are representations. Yeah. So there's maybe row 1 and there is row 2. And when do I say that they are equivalent? Well, I want them to be equivalent if they only differ by a linear character in your one-dimensional representation. So by definition, two such elements are equivalent if there exists a linear character. Let me denote this by IR1G, just a kind of a homomorphism into C star, such that row 1 is isomorphic to chi row 2. Now, if you're fluent in representation theory, you pass this straight away. And if you don't, it doesn't matter. It's some reasonable, tame equivalence relation on this set, infinite set in general of irreducible representations, and a little proposition, which I'm sure Roger Howe could have proved, and Alex Nowotsky at some stage did write down, is if G is an element in this class of class 2 nilpotent groups, then this number, Rn tilde of G, is actually finite. Looking at you, James, anticipating the question, is there any reason to assume that it's finite? Yeah, it is, and it's a little proposition to check that it is. Yeah. Remember the one example that I gave you of the integers so far? I mean, I said that R1 obviously is infinite. Yeah, you have infinitely many linear characters, but if you divide them out, you get a singleton. Yeah, and higher dimensional ones you don't have. So if G is Z, then this Rn tilde is 1 if n is 1 and 0 otherwise. And you would argue, I mean, this sequence we also don't need analytic number theory to understand, but that's not the point. The point I want to make is that this gets interesting already for the integral Heisenberg group. So Magid and Nunley wrote in the 90s a paper on the twist isoclasses, as these things are called, of irreducible complex representations of the integral Heisenberg group. So again, Rn tilde of Hz is the number of irreducible complex n-dimensional representations of the Heisenberg group up to this twist thing. It's finite by this folklore proposition. The question is, what is it? Well, they didn't write it like this, but I rewrite it faithfully. If you look at the Dirichlet generating series, as I advocated before, with these numbers as coefficients, then, and that's their theorem, you get nothing but the generating function over the Euler phi function. Yeah? In other words, so Euler phi is the number of units modulo n. The Heisenberg group has Euler phi of n irreducible complex representations of degree n up to twisting. That's their theorem. And if you take these numbers and you string them up, as I do, you get this expression, and your elementary number theory students might be able to compute what this is. So this is zeta s minus 1 divided zeta s. And if they can't, you point them to Hardy and Wright's classical book, and there are a list of such identities. Yeah. So the point I want to make is that already for a very, very tame group, non-abelian, but just about non-abelian group, this counting problem, counting representations, yields a mildly interesting answer. Yeah. I want to highlight two properties of that formula before I go on, and there's 6 of them over there. Okay. We can go. Maybe the definition of T2 can go. Yeah, we've known the Heisenberg group now. Yeah, so we know the Heisenberg group. So zeta s minus zeta s. I mean, this is a nice formula. Yeah, it's nice enough to have made it into a Hardy and Wright. It's a function that, because it is made up from translated inverses of the Riemann zeta function, of course inherits lots of properties of the Riemann zeta function. Yeah? So in particular, I should give this guy a name. I will call this the zeta function, the representation zeta function of the integral Heisenberg group. Yeah? So this object is zeta s minus 1 divided by zeta s. And we recall that zeta has an Euler product, yeah, indexed by the primes. And of course this guy has, in run over the primes, the local factors look like 1 minus p to the minus s over 1 minus p to the 1 minus s. I mean, that's still not too bad as a rational function, yeah? Rational function of degree 0 in this parameter p to the minus s. Easy to handle. But not obvious, is it? I mean, that paper is a 15-page computation, yeah? And even with hindsight, I don't think it's obvious. The added value of writing down this zeta function is to say something about the abscissa of you can read off the abscissa of convergence of this object, yeah? Abscissa of convergence of Riemann zeta is 1. If you move it by 1 to the right, it's 2. So you know that the representations, or partial sums of the representations, grow quadratically, and you can actually write down complete, precise asymptotic formula for these. I don't want to dwell into this. I would like to bring tensors onto the scene with a view towards being able to prove this result for you either today or tomorrow. Yeah, I would like to show you that the tensor point of view helps us to compute representation growth zeta functions of groups like the Heisenberg group by looking at the right tensors in the right way. That's my ambition. Yeah. And now, as I reckon, yeah, we heard this morning what a tensor is and what it isn't from two different people, so I'm feeling at complete liberty to do what I want. And I also feel at liberty to commit a sin of choosing coordinates. Yeah, I mean, I tell my students that they will pay for their sins, in particular for having chosen a basis when they didn't have to. Yeah. And yeah, I pay for my sins. I want to tell you about commutator matrices. Commutator matrices. Of course, maybe they should be called commutator tensors or whatever, but I'm a man of the soil. I think in terms of linear algebra, and then we take it to tensor world. So G is an element in T2, remember? That means, what this means is really that G is made up from two abelian groups. Yeah? So there's G prime, and that's I assume that this is equal to the center. Yeah? So this is a free Z module. Let me write it as Z to the B. And there's the cocenter. And the cocenter is also a free Z module. Torsion free, because it is, and I will call its rank A. Yeah? So this group G is really made up from a copy of Z to the B and a copy of Z to the A. Yeah? And when I say made up from, I mean the following. I mean this commutator map now is a biadditive map on ZA times ZA into ZB. Yeah? All I have to now, one way to explain to you how this commutator map looks like is to choose bases for these free Z modules and write down structure constants. Yeah, and that's what I'm going to do. So I will choose bases E1 up to EA for the cocenter G mod Z, and F1 up to FB for G prime. Yeah, so these are just, if you want, I mean, these are just elements in Z to the A and Z to the B respectively, which freely generate these two free modules. And now, explaining what this map looks like, one way to do this is to write down the structure constants. Yeah, and by linearity, it's sufficient to tell you what the commutator of EI and GEJ is. Well, it's an element in G prime, and every element in G prime can be written uniquely as a Z linear combination of the Fs. So let's give names to these numbers. Here they are. Lambda ijk is what people would recognize under the term structure constant. So these are the structure constants for G after having committed the sin of choosing bases. Yeah? Okay. And you will agree that knowing these structure constants is the same as knowing this map here. Yeah? Where does the matrix come in? Well, here, matrices. Yeah, I said matrices. I want to introduce actually two ways of making use of this data. And Tobias Rossmann, who is here in the audience, will tell us that these things are dual to each other in a precise sense. But I can still just throw the definition at you. So I will define the B matrix. The matrix B in variables y1 up to yb. So it's a matrix. What is it? Valency and dimensions. Yeah. So this will be a valency 3 vectors, valency 3 tensor of dimensions A, and B. Does that make sense? Yeah. Great. Whatever. This is an A by A matrix with entries which are polynomials, actually linear forms in y1 up to yb. So the yi's are just variables. Yeah, they are variables. I mean, of course they are variables. So how do I define such a matrix? Well, I tell you what the ij entry is. When I write b, then I mean the vector of y. When I write y, I mean the vector of y's. Yeah, y1 up to yb. What's its ij entry? Well, the ij entry is paid to record the structure constants that arise in the description of the commutator ei, ej. Natural way to do this is this: k equals 1 to b. Okay, b lambda ij k y k. Yeah. So I just think of these f's somehow. No, I don't think. I just do this. Yeah, I just do this. So this is a linear form. And now I've described a matrix of linear forms by telling you what the ij and j entry is. Yeah. So for example, for our friend Heisenberg, if G is the Heisenberg group over the integers, there are obvious choices of bases. Let's say E1, E2, and F, and the commutator of E1 and E2 is F. Then this matrix is an A by A matrix. It's a 2 by 2 matrix whose entries are linear forms in B variables. It's antisymmetric. There isn't that much choice, yeah? And the commutator of E1, E2 is F, reflecting the fact that here in the 1, 2 entry, I have the linear form consisting just of the single variable y. And it's antisymmetric because it is. So this is the B matrix for the Heisenberg group. Okay, 2 by 2 matrix. Where there's a B matrix, there's also an A matrix. And this A matrix is a slightly different and for many purposes more useful way of encoding the same data. And I reckon in the language of tensors, I'm just choosing a different axis through which to look at this data. The data are the structure constants, yeah? This is our data. And one way to look at this is through this axis. Another axis can be chosen to yield the following matrix. So the A matrix is, as I said, in a precise sense, dual to B. It's a matrix in variables x1 up to xa. It's not a square matrix, it's an A by B matrix whose entries are linear forms in variables x1 up to xa. And again, I explained what A is by telling you what the IK entry is. The IK entry is J equals, what is it? Yeah, J equals 1 to A lambda ij k x j. Yeah, same data, recorded differently. So if we all could draw three-dimensional things, you said the world would be a better place. I don't know. I'll fail this. So this is my attempt to drawing a suitcase of dimensions A, and B. And so I reckon the B matrix is what I see when I look at the suitcase from this direction, and the A matrix is when I look at the suitcase from this direction. Same thing, different way of writing things down. And you may well wonder, well, why? Why write the same thing in two different ways? And I hope to convince you about this in the course of my lectures. You've been very brave, you know this? I mean, you've been sitting here since 9, yeah? It's almost 12. I mean, I at least I get to walk around, you don't. Who are you? What do we do about this? I'm not gonna torture you any longer. I think. I mean, it's almost lunchtime. Actually, allow me to do. Okay, there's a cliffhanger. Okay, cliffhanger is tomorrow. Tune in again, please, because tomorrow I will explain why the zeta function, counting irreducible representations of the Heisenberg group, is what it is, namely just the generating function of the order phi function. In terms of arithmetic properties of the B matrix of the Heisenberg group. So the B matrix of the Heisenberg group, again, antisymmetric 2x2 matrices don't get much simpler than this. Yeah? There isn't much room. Yeah? Here's something and here's minus to something. So this 2x2 matrix, viewed as a matrix of the linear form, the linear variable y, is the key to understanding why the Heisenberg group has Euler phi of n irreducible n-dimensional twist isoclasses. And by explaining to you why that is, I hope you give me some credit for extending my interest to more complicated commutator matrices. And you will get an inkling, I'm quite sure, how this leads to a result that generalize this result. Actually, I learned this result in Oberwolfer, I think in 2004, pretty much 20 years ago. Ben Martin, group theorist in Aberdeen, I think now, gave a talk about representation growth of these T2 groups. And he showed a very impressive result by himself and Udi Ruszowski. And those of you who know Udi Ruszowski knows that there must be some model theory in it. And there was, yeah. So they used difficult model theory to prove something very remarkable about these zeta functions, which I will tell you tomorrow. And he gave one example, and that was the Heisenberg thingy. So then in the break I said, Ben, this is fantastic. What other examples do you have? And he said, what other examples? I mean, this is model theory. What do you expect? Yeah? This is so then I thought, well, I expect a little more. And that was 20 years ago. And now it's almost 12, and I can finish by advertising an event that you will also find advertised on the web page. So James asked for a bio. I provided a bio. and I smuggled in, and you didn't purge it, an advertisement for an event that's called Combinatorial Methods in Enumerative Algebra. What enumerative algebra is, I told you. Combinatorial methods, I will tell you tomorrow. Anyway, this event is a 2-week program at the ICTS in Bangalore in December 24. It's organized by Angela Carnevale, who's here, Uri, Amri, Pooja, and myself. If you think that this might interest you, I will put this somewhere near the coffee. I reckon that's the attractor, or talk to Angela or myself about this. Sorry?
Do you want to tell anything about applying to it?
No. If you, well, you need to apply for this, and something happens on Friday. Yeah. So if you were interested in this, please apply before Friday, and certainly talk to me if this. Thanks for your time. Have a good lunch break, and see you later.